So I hope you're looking at the lesson yesterday. I'll just load this up because it'd be quicker. Where your priority, of course, was tackling, is that the one? That's not the one I was thinking of, I guess. Must be this one. Priority was tackling the equilibrium force stuff, this with a star. This stuff, of course, you know, is stuff you have to make sure you're familiar with and can recognize things. And the key thing often is in there is like if you give an acceleration, you can figure out F-net, and it's like the driving steps behind tackling the questions. So just a quick check here. You can hear me, right?
Yeah.
Thank you very much. Thank you. I asked if anybody needed help, and there wasn't any responses, so I wanted to make sure you did hear that opportunity. So this might be one of the last lessons where I'll be saying, okay, well, we're reviewing a lot of things, because we're going to start getting into what's called non-inertial reference frames, and that leads to circular motion. So after that, it sort of gets into new stuff, like the lesson here on centripetal acceleration. We're going to use that fancy word soon. So before we get to the new stuff, though, let's do a little bit of new stuff to do with this review, to do with friction. So I just want to remind you that we've seen in the past that friction is mu Fn. The friction force is basically a percentage, right, of the normal force. So we know the normal force is just that like contact force between this between objects. So this is basically contact force between objects. And then mu is like a number, right? So basically this is, you could think of this as the percentage, right? So basically friction force can be a certain percentage of the normal force. So you'll see, just to remind you, like friction coefficients can be lots of different values. So if you're looking at oak on oak, then you've got 0.30. So essentially the kinetic friction force, it can be 30% of the normal force, and the static friction force, which I'll mention in a second here too, can be 40%. And you can actually have bigger values than like the actual value. You can have like 107%. So a little bit more than the friction, than the actual contact force between them, which is strange. It's not usually a lot bigger though, but it can actually be more, and you get the more force from like the rubber on asphalt when it's dry. You're actually like grinding the rubber off and leaving a patch on the ground, you know, stuff like that, right? So that's how you can get more force than the actual contact force between the substances. So I'll tackle the right side in a second, but let's focus on the left side first. So static friction is the friction that's possible when it's not moving. So in contact and in zero velocity relative to between the two blocks, I should say, or two objects. So that's like mu s, it's listed as, and that number is bigger, if you recall, from grade 11, because the friction is actually coming from like interactions between the electric fields of the atoms, and so you have more bonding between the molecules, attractions to positives and negatives, and so on. Sort of when it's stationary, and when it's moving, you have kinetic friction, and you've got an average of all of those kind of electric bonds that are interacting and breaking and making and breaking bonds. So the kinetic is smaller. So I should add that in there too. The kinetic is smaller. So the example of oak on oak I used was, this was 0.3. No, this one was 0.3. This one was 0.4. So yeah, this is oak on oak, oak, oak. And so the other thing we got to watch for is to keep in mind the reality here that friction force can be up to and including that mu Fn value. If acceleration is 0, you end up with the friction force equal to the applied force, and that comes from F net. equals FF plus FA, right? Talking about like F net in the x direction, applied force in the x direction, friction force opposing that motion, and so on. And so if you have an acceleration of 0, as we said a bunch of times yesterday, then your net force is 0, and that just leads algebraically to that equation. So really, actually, you'd actually have a minus in here, right? But the idea is this is was meant to be the absolute value of the friction is equal to the absolute value of the, just directions not being worried about, just talking about the size of it, essentially. So we know that the friction force, we're saying here, I'm trying to emphasize mainly that it can be up to and including that value, but it can't be more. So for example, if you have a friction force available of 100 newtons and the object is just sitting there, and you come along and push on it with 80 newtons, obviously you're just not going to move the thing, right? And so you got to be careful not to have a weird calculation result where you claim mathematically that you think that this thing's going to have a net force on it of 20 because you tried to push on it, right? And then that would, a net force of 20 would lead to an acceleration. So picturing a heavy object, sitting there, you come along, you try and push on it. You weren't able to push hard enough to get it going in the direction you're pushing. So instead it accelerates towards you. No, that doesn't happen, right? So basically you'd have to limit this friction force in a case like that to match the applied force. And then that gives you the 0 net force and the 0 acceleration that makes sense, the object you didn't manage to push it, right? So what happens if the available friction force is greater than the applied force? The friction will only match the applied force. The thing won't accelerate. Any questions about that? All right. So main thing you're jotting down, just to remind yourself, is FF equals mu of n. And there's two different versions, right? There's you could do like a little arrow to the mu and put like an S and a K, reminding yourself of that. So this page summarizes the static part, the static forces, the friction that's available when it's stationary. So you got a block sitting on a table here, and this Fs represents the static friction. And they're saying, you push with 5 newtons, it doesn't move. Static force is 5 newtons in the opposite direction, giving you a net force of 0, no acceleration, right? If you push with 10 newtons, still doesn't move. Then you're like, oh, you have 10 newtons back. Eventually, if you push hard enough, you're going to just start to get it to go. And then when you get to that limiting static friction value, that's the value we're talking about. They're writing it as this. Of course, I think we would normally think of it as like the static friction force. They're saying SF for static friction equals the static friction coefficient times the normal force. So for some reason they're writing it like that, but yeah, I wouldn't worry about it too much. Like this is the same as what we said on the other page. So coefficients are just a bunch of values you could look up. You can Google it. It'll be given in a question, whatever. You're not required to memorize those things. Just basically know the idea of how to use them. So this oak on oak example, I'm just going to show this one because it's totally review. But calculate the applied force necessary to get it moving. You just have to figure out what the normal force is. It gave you the force of the mass of it. Someone's microphone's on there if you want to. We got. There we go. There we and turn it on, of course, if you want to ask a question. So you got your mass, and so you're going to just calculate the gravity force. So they're saying here, the way this is written is like, recall that the normal force equals the mass times the gravity. That's coming from acceleration in the y direction equals 0. So F net in the y direction equals 0. And so, since we know F net equals the normal force and the gravity force added up, and this is 0, that leads to this statement. And they are saying like absolute value there, so you don't have to worry about minuses. Oops, wait, now what? Static friction, mu Fn. Oh, this part, sorry, I went to my arrow to the wrong spot there. I was like, wait, that's not with friction yet. So let me just undo my arrow here. If I can ungroup and delete. right? Or it was just supposed to go to the FG, FN equals a FG business. So they're just saying like mu FN, right? So they're just doing the mu times the value. So there's your FG value that we know it's equal to, and you just do mu FN. So you're just calculating a friction value. So that needs to be super straightforward. Moving on, so that you have that basis or that base knowledge in order to be able to tackle the weirder questions. Any questions about that one? All right. To make this page a little more clear, I guess I could do Fn equals the negative Fg, and then, you know, that. Yeah, so there's your Fg value, right? Absolute value of Fg. All right, so the question of what happens if the force was less than the available static friction force, you need to recognize, you're like, oh, okay, so I'd have F net equals the friction force plus the applied, the applied force. And basically here, you know, you don't want to be saying, okay, I've got 300 here, and my friction force we calculated can be as much as 392, right? So this minus 392, just remember, this is as much as, but would only match the, or let's just say FA, right? It would only match the 300. So it's going to right there. So you're going to basically say, okay, yeah, it could be 392, but it's really just going to match mu minus 300, giving us a net force of 0, right? So acceleration would be 0. We're not pushing hard enough to move the thing, and that's the logic that you need to have be obvious to you in that case. So I just emphasize that if you're pushing not as hard, again, just because it's a pretty bad mistake to have if you think that you're going to push on something and as a result it's going to accelerate towards you because you didn't push hard enough to get it going. That would be ridiculous. So kinetic friction, we're talking about as the thing is moving, you've got this sort of average of the electromagnetic interactions and so on, but overall it's smaller. And so this is just the the force of friction. How did they show this? F kinetic friction. I guess I just normally do FK, but they're doing KF kinetic friction. And so that's your Fn, same as on the other pages. They are doing absolute values there. They're being a little bit more careful in a grade 12 context here to recognize that, you know, that it's not about directions, it's more about the values. So the new stuff, we'll start to tackle new stuff in this question here. And so we're going to have what do we have? A ramp, right? Hold up an 11-degree slope. So we've got a ramp situation. So things to watch for in that is that this changes the normal force. And since the friction force equals mu of n, right, it's going to change how much friction there is as well and so on. So you got to watch that. So they're giving, of course, like I said, you're always just kind of just given this coefficient. So we just have to analyze this out, right? So some of that stuff I just said in red there is probably going to be here, where we're like the normal force is different than usual. The normal force is perpendicular to the ramp instead of just like perpendicular to the ground. So the value of the normal force we need it, of course, so you can calculate the friction force, and then you're going to work things out after that, right? So this part here is about how to get that normal force, right? So you got acceleration in the y direction. Let's picture the ramp, 11-degree ramp, right? So is that what it was? Yeah, 11-degree ramp. And we've got a gravity force down like that. We've got a component of the gravity force in the direction of the ramp, and a component of the gravity force perpendicular to the ramp, right? So basically our analysis here about acceleration in the y direction being 0, like this thing's not, I'm going to put it here, it's not lifting up off the ramp, right? It's not accelerating up or down from the ramp. So not accelerating up or down, off or into, I suppose, the ramp, right? So this thing is going to be, if it had any motion at all, it would be accelerating like up or down the ramp, not up or down off of the ramp. Now this thing actually has constant velocity anyways, so especially in this case, it's obvious there isn't any acceleration. But even if there was an acceleration down the ramp, for example, right, there would still be this. You'd still have no acceleration up off of the ramp. So I'll get rid of that because in the context of this question, of course, we don't have even acceleration up the ramp or down the ramp. Anyways, so that leads to, it's going to be on the next page, I'm sure. It's always being redundant lately, but F net in the y direction would be the gravity y component. That's this thing, Fg y component, plus the normal force, right? So the normal force is the one that we need to sort of label in here. So picture that normal force balancing that gravity force y component, and you can picture then why it doesn't have an acceleration. Okay, so we've got this being a 0, and so we're getting the logical result that the normal force, when we subtract out the Fg y component, right, the normal force is the opposite of that gravity force. Let's give you a moment to digest that. It's going to be, like I said, it's probably going to be on the next page anyways, but I think the next page actually we're analyzing the x direction stuff first, maybe, if I remember right. And then we're looking at the y direction stuff. So you'll actually see this analysis again. I'm doing that on purpose because it's important. You need to be able to do it, right? So I'm trying to help that way. So they're saying the analysis here, as soon as you see this thing, Sarah was all over it yesterday for sure. As soon as you see that, you're like, ooh, I know that we've got 0 acceleration, therefore we've got 0 net force. So that was awesome that you're showing that that's like definitely the thing you want to recognize, right? So net force is 0 along that x direction. And so now you just have to think of what forces there are, right? So this thing is being pulled up the ramp. If we drop back to the question here, it was we're being pulled up at a constant velocity. So that's why the friction force is down. Right? That friction force is against the direction. We've got a velocity this way, and so we've got a friction force against the motion. So that helps you figure out the direction of the friction force. Clearly, it says there's a tension force, an applied force, if you will, up the ramp. And then we already talked about the idea of the gravity force down. We've got the Fgy component here. And we even have an Fgx component. That didn't show up as obvious as I'd like it, but it's there. So in the x direction of stuff, we're going to need to look at those forces, right? If we're talking about x direction, along the x-axis, we're talking about these forces. So we're going to list those. Let's see what we got, right? So we've got, first of all, we've got that we know that it's 0. That's, because it's all constant motion stuff. If you were given a mass and given an acceleration, maybe you'd know like ma as a number, right? So this is 0, or could be, ma, right? Some number if there was an acceleration. But we have our friction force, we have our gravity force, and we've got our tension force. They are doing my less preferred version of things here. You know what, I can fix this simply by saying we've got this force, and we have, this force, And we have, like just adding up all the forces, right? So I just kind of prefer, in most cases, you can't always do it, but in most cases, I prefer just putting in numbers, positive or negative. But you can see here, like they're putting in symbols, so you kind of do have to have the negatives in to show the directions. So we've got our tension force. The angles, are we okay with the angle? This angle in here is 11 degrees. It's supposed to be, I'll just put an arrow there because I can't quite show that well. We have 11 degrees there. And then if you look, however you want to look at this, but we've got certainly a right triangle here, 90, 11, and then the complementary angle. But then there's that complementary angle, 90 degree happening there as well. So that's going to be your 11. Anyway, so that's your 11. And so that's why they're doing, in this one, you can see they're doing mg sine 11, because this FGX is opposite, right? So it's going to be the FG sine 11 because it's opposite to the 11 degrees. So we are given a mass. They're kind of just going with variables for now, but obviously we could have at this stage put in the 60 and the 9.8 and so on. And this is where I might have put in a minus 9.8, and that would give the minus, right? Appropriately.
What's that symbol with the K there in the substituted equation?
Right there.
Yeah.
That's your mu, right? That's your coefficient of friction. That's your kinetic mu K equals your kinetic coefficient, right, of friction. That is, sometimes writing on this works out well and sometimes it doesn't, but I'll just go back to the table here, right? That's your friction coefficient that they gave you, right? Listed just as a variable.
All right.
Okay. So that leads to what here? That, so what would we have? We'd have number, I guess we'd have all the numbers at this point. Why isn't that solved out at this point? Wonder if maybe we, oh, you know what? We don't actually have the normal force yet. So we had to actually, I would have started with this personally, right? As I alluded to in my hints and so on, it was like acceleration in the y direction is 0 because we need it for that friction force. We're going to kind of do this first normally, but I feel okay with showing you other ways, because this is obviously just captured from another source, and this is the kind of thing you're going to see, and you need to be able to weed your way through it, right? So I don't feel the need to like make everything be the sequential order I prefer, even though of course that's what I'm hoping you're going to do, right? So what we talked about already, the net force in the y direction up and down, off of the or into the ramp is 0 net force. There's 0 acceleration. So basically we're saying, oh, well, we know the normal force is equal to the FGY component, which is the mg cos 11. If we look at the angle here, we're adjacent to, right? So this FGY component is FG cos 11. So they're putting FG in as mg, which clearly we actually know both of those numbers in this case, right? So we can figure that out. So they're actually kind of combining things here. They're saying, it makes it a little hard to follow. So they are solving for the tension force and therefore plugging things in and getting it. So what I might do instead for you is show that this equation, let's think of this as a number, right? We've got the mass, which is, I'm trying to remember here, 10, 60. It is 60. 9.8 cos 11. That's just going to be a number, right? And so if we think of this formula here, I might just go with that one. So we'd have our negative number here of the 0.10, I believe they gave us for the coefficient of friction. Yep. And we'd have times that normal force, which we've calculated to be this number here, right? I might as well just copy that while I'm here. save myself the pain of trying to write on this little screen, right? So there's your normal force. Let me just underline with green there so you can see that's Fn. And then we have the minus the 69.8 sine 11 plus tension force equals 0, right? So basically at this stage, you can tell algebra, you're just going to solve for the tension force. Okay, so that's what they've done in that other slide. I feel like it's so much easier to follow. So I wanted to just help you see that version of things where they're putting that normal force in, but they're solving for the tension force first, making it harder to follow algebraically. But there's the same stuff, right? There's the 0.1, the 60, the 9.8, the cos 11. It's all the same stuff. But anyways, so they just numerically solved and got a value of 169.915 is what this one would be as well. On this number here, there's whatever that was, 169.915. Okay. And of course they're rounding to 2 significant digits because they're trying to be careful with that all the time. But I don't want you to have to stress about it all the time, but be aware of it. The idea of the 3 significant digits actually they had there. So they did 3 significant digits. If we're reviewing that just quick here, because there's 3 there, but they only gave it as 11, right? So that they really should have given that as 11.0 if they want to say, yeah, we got to keep even here actually. If they're keeping 3 significant digits, drives me crazy when they try to be super thorough on something like that. Why else are they rounding like that, right? But if they're doing that, they should have either had the extra decimals earlier or not had the 0. Anyways, so I'll keep reminding you of the significant digit stuff just along the way to help you remember it. Any questions about that question? So remember, I would typically personally sort of start with this and get that normal force value. Then when we're analyzing the x direction stuff, I would be able to put that normal force in right there and then just work and get a tension force. Yeah. Okay. So I feel like, I don't know, whatever. I have to reorganize this a bit to make it easier to follow overall, but like I said, you're going to see ugly versions of things as well. Anyway, so moving on, if we don't have any more questions about that one. Newton's laws with friction. So this is grade 11 review stuff as well. So I'll just show it as we go. But for example, if you're pulling at an angle, the key to recognize about pulling at an angle is that this changes the normal force, right? So you have to recognize that. So it changes how much an object is resting on the ground. If you're lifting it a little bit, or if you're pulling it downward at an angle, you're making it hit against the ground even harder. So the kind of diagram we're looking at is we've got the free body diagram, we got the dot, we've got gravity down, we've got an applied force on an angle, and we've got a friction force backwards, we've got the components of the applied force, and then so on here I'm showing like the normal force as well, trying to like picture how much it would be. So overall, the red is basically the overall idea that we must have a balanced situation. So let me just show with big purple here that and that are balanced, right? So they're balanced. We've got the overall forces are the same. So what you can picture here, because I have it all shown, is that this applied force upwards and the normal force, so that's it right there, and the normal force are combining to be the same as that gravity force. So the only thing I don't like about what my slide is left as here is it says Fn equals negative Fg, but it should have been in there Fn plus this combined force. So why don't I just move that over here? Right, that combined force is equal to the opposite of the gravity. So the normal force and the applied force. You can see how logically they're going to combine to be, the opposing force to balance things out. So of course we're looking at free body diagrams to help us understand, and so on. So that normal force, to really analyze this out, you're saying, okay, we're not accelerating relative to the in the y direction. That relies on the question being clear that the thing's being pulled on an angle, and they might say causing acceleration sideways. So I'm going to say causing acceleration horizontally, right? This is extra details that would be included. What that means is you're not lifting the thing. You're not accelerating it vertically. So you're not pulling too hard and lifting it. So acceleration in the y direction is 0. If acceleration in the y direction is 0, of course, F net in the y direction is 0. So if F net in the y direction is 0, you've got all of your forces in the y direction. You've got the gravity, you've got the y component of your lift force, and you've got your normal force. And so you're able to solve for that normal force. So this question, let's go with it. So basically here you're going to have a negative number. So I'll try and help make sense of what I've done here. So this is going to be a negative number because it's down. This is going to be a positive number because it's up. And then you're wondering about the normal force, right? So you end up with, we're saying here, take away the gravity force, right? So that ends up being subtract that negative number. That's this part. And then we have subtract that positive number. So this one's just analyzed in general rather than having actual numbers that we have to worry about calculating. The end result is that we have a normal force, and picture how we'd end up with a positive number, take away a number, we'd end up with a smaller normal force. That makes sense because we're lifting it a little bit, right? So I think I didn't really have an example of a piano. You drop, you're helping move a piano and you let it down because you're exhausted and it's on your foot. And you're like, help me. So if someone comes over and pulls up on the piano a little bit, that's going to help you, right? It's going to reduce that normal force. Anyways, so friction force would be the mu Fn value, right? So you'd be able to figure out the friction force. You'd have a number for the normal force. And you'd be able to say, and the acceleration in the x direction, you'd use your applied force x component and your friction number. Why is that going into the minus? Well, just obviously the friction is going to be against the motion, right? So you get a value, and then F equals ma, and so you can calculate the numbers. You can calculate the acceleration. So that one's walked through ideas-wise without having to worry about crunching numbers, which in the long run, eventually that's going to be like, okay, I get the concepts here. I'm not worried about, I'm not bogged down with numbers. Right now, I suspect it's probably like, a lot of letters, right? But you need to get to the point where that's actually a helpful thing, or at least you can tackle it without numbers. You'll see. All right, so that's review of that. Well, it's a little bit, that's totally review actually. We've done the pull at an angle thing, right? So the new part comes more so with the ramps. And so this is the question where I'm saying like the grade 12 kind of twist here is that, I didn't give you a mass, right? But that mass doesn't matter, right? It's, like the more mass there is, the more gravity there is, but there's also more mass to try and accelerate. So there's more force, but there's also more mass. So acceleration result is the same, like all objects fall at the same rate. So this question, as we work through it, will seem a little weirder, a little harder, because it's like an M instead of an actual number. So, you could, I suppose, put a number in for it and it'll work out. But you grade 12 level here, you really want to be able to just carry this out without a mass number, mass value. Sounds too much like chemistry if I say mass number. All right, so we've got this thing, we've got this ramp, and it's sliding down the ramp is the wording you had been given. So like you're choosing your x direction in the direction of the acceleration. So let's point out, you're told this thing's sliding down the ramp, accelerating down the ramp. You'd also have like a y direction as well. So, you'd have like an x and a y direction like this. My computer's at it again, moving stuff around on me here. All right, so there's that direction system I'm mentioning. And there's our free body diagram. So we've got a gravity force down on it, which we can't say the value, but we can say that it's 9.8 m. I wouldn't always put a minus here, right? Because the arrow clearly shows down. So I might prefer to have that just be 9.8 m, but we know that when we put it into an equation, it has to be a negative value, if that makes sense, because we're thinking about directions, right? So far, we got the idea that we've got these components of the gravity force. We've got the angle of the ramp listed. So that's pretty much all we know. If the thing is accelerating down, we could, I suppose, put a friction force on here as well, right? Of some sort. So, there's going to be a FF on here as well. So we know that the x component of the gravity, if we're looking at angles here, this is, you probably just sort of get used to it by now, that this is the 29 in here, right? And so we're talking about the x component in this triangle is equivalent to this one here. And so we're on the opposite side. Right, we're opposite to that 29 degrees. So you can use sine 29. Yeah, so you have a value sort of there, 4.75 m, right? We're evaluating what we can, but we don't have the m value. Alternatively, it could be totally in general, 9.8 m sine theta, but that would be even weirder. The y component, very similarly, 9.8 m, in other words, gravity times the cosine of the angle, because the y component is adjacent to this, right? So this is adjacent. Grab green if I can here. Adjacent to the angle. So that should be, that needs to become something you just start to be able to do without too much worry. I think the main thing for us right now is just to get the hang of that, which angles which, maybe, to get us on the right track. So I'm saying here that you have to try and get that friction force, right? We know friction equals mu Fn. So first we have to think about what that normal force is, right? So the normal force comes from knowing that the acceleration in the y direction is 0. It's not jumping up off of the ramp because it's sliding down the ramp, right? So the acceleration in the y direction is 0. So the net force is 0. And so you've got a net force is 0 equation, okay? The forces in the y direction, you've got the vertical component of the gravity, and you've got a normal force, which isn't drawn on here yet. So we could do that too. It's probably better to have it right away, but it's not necessarily obvious that it even exists, right? So as you analyze through, you start to recognize what exists and you label it on. So you got a normal force, and yeah, so we know based on the fact that it's 0 acceleration vertically, that they are going to be adding up to 0. So that gives us that the normal force is equal to that 8.57 m. Just pausing a little bit now and then for you. Trusting someone's going to key their mic if they need me to put the brakes on a little. So what can we do with that normal force? Of course, we can calculate that friction force, right? So friction force equals mu Fn, which gives us a 0.11 times that 57 m. So now we got a negative 0.943 m. Again, usually this might be in as like an absolute value of things, in which case this would be listed as a positive, but when we put it in, we know to put it in as a negative, right? So you have options for how you take care of the negatives, as long as you end up with the right value, right, when you plug it in, right? So acceleration in the net, in the extraction is obviously to do with the net force in the extraction. So we need to look at what the net force is in the extraction. Looking at your free body diagram, you only have two forces in the extraction. You've got the gravity component down the ramp, FGX, and you've got the friction force that's going against the motion. So we've got the gravity force, which is the this one here, the x component, the 4.75 m. That's going to go it's going, that's in the direction you're actually wanting to accelerate, right? Or you know it's accelerating, so that's in the positive direction. So I'm going to emphasize that by putting in a plus sign in here. Right, so this is a plus right here because it's, you know, in the direction of the ramp. It's in the positive direction. Trying to avoid saying down the ramp because down always makes people think negative, right? So it's in the direction it's going down the ramp. But yeah, so the other one we have and a negative force, right? So we have this friction force. So this one's going as a minus, of course. We have basically and a negative value, so it ends up being, you know, and a negative value ends up being a negative. Of course, it's against the motion, right? Against, that's supposed to say against that motion down the ramp. So anyways, we end up with a net force of this value here, 3.81 m, right? So finally, this m that's antagonizing us all the way, we're like, ugh, variables are in there and have to carry them around everywhere, but this is where we get to have that m disappear, because net force equals mass times acceleration, and we know the net force is equal to 3.8 m. So m's cancel out. If you had more mass, you'd automatically have more force, right? So the amount of mass doesn't matter. So we get an acceleration of 3.81 meters per second squared. So that's obviously, if you're given the mass, even easier, because you wouldn't have had this stress of you know, these variables. So if you can follow that with me, then you can just plug numbers in and do it. I wanted to show this version. If I show the number version and then expect you to be able to do this on your own, it doesn't work as well. Any questions about that one? Do we need to stay on that page any longer? All right. Okay. So this one, maybe, you know, this is direct review. I was going to remove it from the lesson actually. So, you know, I don't want you to think of the quantity that's here as a negative thing. I want you to look at it as like, oh, at least there's a review there of this block on a block kind of question. So you have to remember that, you know, you're asked like how much force can you apply to the bottom block without the top block falling off or sliding off, and you have to remember that you have to figure out how much friction is there, figure out how much acceleration this block can get from that friction, set the acceleration of the system equal to that value so that you're not accelerating it too much, right? So I will just reveal these steps within the PDF file if you feel you need a reminder of that. Right? So we need that normal force field, friction force, and so on. But the key steps I outlined was, yeah, the idea of, you know, how much friction force is available here, because then that'll tell you how much, let's do F net equals MA, right? So the net force on that block is the friction force, and the mass is m2, and so this allows you to figure out the acceleration possible. And then, yeah, you're going to set the acceleration of m1 plus m2 equal to this value, right? and then basically solve for what applied force is there. So that's the idea of what's going on there. So you just have to make sure you can do that. So there's that friction force, and there's the acceleration of that, right? The 4 kilogram block on the top. And we're saying, oh, it accelerates at 1.96, right? So the concept is that's the max acceleration of the system. So you set that true and figure out what your value is. That gives you an idea of this question and helps you. There's that entire system acceleration business again, the entire mass, and the force that you can push with. So it's just a classic example that comes up in friction questions, and we did it thoroughly in grade 11, and so I'm just giving you a chance to have an easier way to review that. Yeah, the questions can seem. Do we need any questions about that one? I'm not really obviously giving enough time to copy it down. You're going to look at it later if you need it, right? So in the homework, if there's a homework question about it, you need help. It's there for you. This one seems a little different. The questions can look a little different, right? So this one has it gives you an angle. So the angle of the ramp is the one in the bottom here. When I was looking at it earlier, I was thinking that this number up here, but it's obviously the angle here. Let's go like this, right? We've got angle theta, and so we've got a line like that, a line like this, right? So it's like, I don't know, 17 degrees or something. I think they use 17 and a half, right? So that's the angle that it just starts to move at. And they want you to determine the static coefficient of friction. In other words, the coefficient of friction to do with when it just manages to start to move, the force that just makes it go, right, is your static friction force. Once it starts to move, the friction force amount becomes less because it becomes kinetic friction. Anyway, so basically they're telling you that this is the configuration to just get it going, so you can actually calculate the static friction. So just reviewing those ideas again with you here. So the angle is 17 and a half, like I said, and they're saying the force, the instant before it starts to go, right, is your static friction force. So they're saying, okay, well, you've got your normal force is FGY, and your friction force is equal to the X component of the gravity. So in this diagram, maybe I'll do a new diagram, free body diagram, here it is. So you've got a component of gravity this way, FGX, and you've got a static friction force, and you've got values. So it's kind of weird that they don't have these balanced. Like this should have been like this, right? So it's like just as it starts to move, as soon as the angle gets a little more, the gravity gets a tiny bit more than friction force, and it starts to actually go. As you're varying the angle, that actually changes the normal force, which changes the friction force, right? So it's kind of all related. They are showing that angle 17 and a half, like we would have analyzed. So there's your kind of reminder that you've got this like ramp situation, and you've got your 17 and a half, and you're matching 17 and a half in that triangle to the components. So they are starting with that one for some reason. I don't know why they do that. To me, eventually they get to. Oh no, they are because they're going for the component itself. I would start with this one, of course, right? F static friction equals mu s Fg, or Fn, I should say. And so that's leading to the static friction force divided by, oh boy, the static friction force divided by the normal force. Right, so if you want the static friction, they sometimes start with that in other questions where they should just, in my mind, start with the friction equation. But yeah, so they gave us, again, in this question, notice there's no mass given, right? Turns out it doesn't matter, of course. So you can tell the masses are going to cancel out. Even the g's are going to cancel out, and you're just left with the sine of the angle over the cos of the angle. So those came from the idea of the x component being the sine, because we're opposite the angle, right? So this is equal to, that was supposed to be OPB. This is FG sine 17.5. So there it is. And the normal force idea came from this thing being the FG cos of theta. What they didn't talk about was the idea of acceleration in the y direction 0. And so yada, 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 as usual, if you're good with it now, the normal force equals the opposite of that, right? Maybe I'll show it one more time here. That gives F net in the y direction equals, what do we have? The normal force plus, give myself a little bit more room. Really need to lock that in place. All right. Plus that FGY. And so my normal force equals the negative FGY. Right, so that's this thing here, like our normal force is the FGY component. The FGY component is based on cos because it's adjacent to that angle. And again, we're talking about, they're doing absolute values right off the bat there, right? The same as we would be thinking of as well. But anyways, yeah. So that gives us sine 17 over cos 17, which you might remember is actually tan if you wanted to do it that way, or you could actually calculate the numbers. That's using the trig identity. So I'm wondering if maybe you might find it kind of neat to see the trig identities being actually used. The only advantage, by the way, of that is in the old days, this idea here is when you look up values for sine, cos, and tan in a big table of values, because calculators didn't exist at one point to do this. Instead, they had big tabulated values that someone painstakingly calculated out. So you use the big table of values from a book. And so that meant you only had to look up one value instead of having to look up two values and then try to do a long division of them. Oh my God. Right. So this is an old-fashioned thing. Could you just calculate these numbers? Of course you could. And divide them and get the answer? Of course. So in case you're wondering why it's thought of as better to do tan, it's just sort of historically more the way it needed to be done, really. So that's the angle that it gets going at business. What's this one here? We have a ramp 30 degrees. Yeah, they're asking what rate it accelerates at. If you have a 50 kilogram crate, 30-degree angle, and coefficient of friction. So once it's sliding, it's got a 0.42 coefficient. So you just need to be able to figure out the acceleration. So all the same stuff. We're going to figure out the normal force to be able to figure out the friction force. And then obviously figure out the net force in the x direction and figure out the acceleration. So I feel like maybe I should just reveal this one, or like for you to look at later. I've done enough there, but I would probably, like I said, start with this, right? So I'll jump down to where it shows it. But first in my mind is get that acceleration in the y direction equals 0 hammered out. That normal force, free body diagram, and that the y direction up off the ramp, it's not jumping up off the ramp, so the acceleration is 0. So we've got the y component of the gravity and the normal force being the only forces that are vertically on this thing, right? In that y direction. And so we've got that being 0. This should be a plus in the middle there. I suppose if I undo this, it's going to go too far. Yep. So erase, hope for the best. So yeah, so that gives us, the normal force equals that negative of the gravity force. And then you're going to say, oh, well, my F equals mu Fn stuff. Right? So remember, it was like the size of the friction force equals the coefficient times the size of the number, right? So analyzing the diagram here, we would say 30 degrees. This is going to be 30. And so this F GY is FG cos of 30. I had to just pause there to say cos because I need to look to see that we're adjacent. So you can tell that that would give you a number, right? So you'll see that kind of calculation later where you're going to have your 0.42 times your mass was, I forget, 50 kilograms, 9.8, and your cos of 30. So it actually gives you the friction value to actually plug in. Anyways, so don't like that they start with the X personally, but anyways. So X direction stuff, so eventually that friction force is going to go in to there once you analyze it out. So there it is, the mg cos theta stuff, just like I had, right? All that, it's just a little harder to follow. It's all in general, and they're saying like cancel m to simplify. So that's kind of, you know, I was going to mention actually, is it kind of weird that sometimes they give mass, you know, and sometimes they don't? So this do we really need it? The answer is, you can tell down here, canceling m to simplify, right? You didn't actually need it. You can divide out everywhere, and it does cancel out. So mass wasn't even needed. But if you did calculate this out as a number, right, then you'd need the m to stay in the other number, depending how you did it. Okay, so if you did it my way of actually calculating a number here, but if you left this as an m in there instead of a 50, of course, it would still just cancel out. So anyways, that gives you an acceleration value. So run through that as a review as well, and we're good to go for friction. The only thing that was new was about the ramps, right? We had already done pulling at an angle, but ramps changed the normal force too. So that new part there, ramps changing the normal force, might be a page you might need to focus on. Questions about friction? Just have to review them. And then if you have questions, I suppose you can do the extra help session or ask tomorrow, of course. Smaller number set there because it's just only friction that we're reviewing. But, and again, in here, you know, some of these are ramps, some of these are pulling at an angle. And if you see it, if you do one pulling at an angle question, you ace it. Then the next two that are pulling at angles, maybe you can save yourself some time. Skip a little bit. All right. So I'm excited to get into like kind of newer stuff. I've already alluded to this non-inertial stuff a little bit too, but we're working towards circular motion and understanding how to analyze it. So we're talking about non-inertial reference frames, and I've got a story, partially true story actually. So the story is about me and my first dog, Lucky. All right. So Lucky and I once had a dog named Lucky, and Lucky was a lab border collie mix and very smart. The joke about dogs is like, how many dogs does it take to change a light bulb? And said, well, if it's a border collie, just one, and he'll rewire all the faulty wiring in your house while he's at it, because border collies are really smart. Anyways, so Lucky was with me as we were driving to the dump. I had to go to the dump every Saturday to drop off garbage back in the day. We weren't living on Devil Lake. So Lucky noticed something very disturbing on that drive. The recycling bin next to him in the back seat of the 99 Chrysler Cirrus, just to visualize things here, this sedan, four-door sedan that we had at the time, inexplicably began accelerating sideways, right? Lucky's riding along in the car. All of a sudden the cans, like the bin tips over and the cans come rolling towards him, okay? So Lucky notices that without any external unbalanced force to cause these things to accelerate towards him, they were accelerating. So Lucky found that disturbing, because like I said, he's pretty smart. So he found that disturbing, and he found comfort by jumping into my lap. That part's true. The drive to the dump was true. The cans falling over was true. Him jumping into my lap is true. The part probably not true was him being nervous about it because of it not having an explainable force in that reference frame, right? All of a sudden these cans are flying sideways and he's like, what the heck? It's like magic, right? So I jokingly, right, described that he recognized that and it was nervous about it. So once I said to Lucky, you know, once I explained that we were turning a corner and that the recycling was simply trying to do what? Did the recycling actually accelerate towards him in terms of the Earth reference frame? What happened was we were driving along, the car and the recycling and Lucky and me and everything was all driving along at whatever it was, 50 kilometers an hour. And so I go to turn a corner and I turned, if Lucky was on the driver's side, I guess I was turning towards the passenger side. If you can picture it, the cans tried to stay in a straight line, tried to keep going straight forward, which of course the car turned out towards the passenger side. And so relative to the car, the cans seemed to come towards him, right? So when I explained that recycling is simply continuing in a straight line motion due to inertia that it had before the car began turning the corner, the car, of course, does have an external line balance force to cause it to accelerate, thanks to the tires. Lucky felt a lot better, but he rode the rest of the way in my lap just to be safe. He actually did. He rode to the dump in my lap. It's like, good enough. Lab border collie mix, not a super small dog, but he was good. So he just sat there. Anyway, so the force that would seem to be needed, okay, in that context, all of a sudden the cans are accelerating sideways in the car, right? So it seemed to Lucky, or it would seem to anybody, that they would need a force to accelerate sideways. And so I jokingly saying that, of course, Lucky noticed that was missing. And that force that he's noticing is missing is often referred to as a fictitious force. Okay. So there was like, is there actually a force needed to accelerate those cans sideways in the car? No. It's fully explainable based on the actual motion of the car turning a corner, right? You are going to see, though, okay, that these fictitious forces can be included in real free body diagrams, and they will make sense. So I'm going to try and put that all together for you gradually over the next 3 lessons, actually, starting it today. So inertial reference frames, just in case you're trying to get this under control, inertial reference frames is normal stuff, right? You're talking about a reference frame relative to a maple tree anchored to planet Earth. There's no accelerations going on, right? So all your laws of motion make sense in that context. An object isn't going to accelerate unless it has an external force on it. So you can tell, like, you push on it, it goes, whatever, right? So inertia and the second laws and all that stuff, all are obeyed. In fact, all laws of physics are obeyed and are identical in all reference frames that are not accelerating, including if you have constant velocity. So even if you're inside of a vehicle traveling really fast, think of traveling along the 401 at 100 kilometers per hour, because of course that's the speed limit, so that's what everybody drives, right? If you have a ball in front of you in your lap and you toss it up and down, you can play catch with a ball inside of a car that's traveling at constant velocity. It would be totally normal, right? Other than bumps and jiggles and turns, right? Those are accelerations, right? So if you're not accelerating, you're traveling at constant velocity, all the laws are the same. We are going to rely on that huge later on in the course. Einstein's work called special relativity, we're going to tackle later, is based on this fact. Okay, inertial reference frames, all the stuff we've talked about previously makes sense. What we're working towards tackling here is non-inertial reference frames, which is when you're talking about a reference frame, such as a car you might be traveling in that's turning a corner, right? A reference frame that is accelerating. So we're talking about reference frames that are accelerating. So in those cases, first and second laws of motion, inertia and forces needed and so on, are not obeyed. Okay. So for example, the cans didn't just stay at rest relative to the seat in the 99 Chrysler Cirrus. Instead, they accelerated sideways towards Lucky, scaring the crap out of him, making him jump to my lap. In order to fully describe motion in a non-inertial reference frame, you either have to, so I should say you either, right, need to consider the accelerated motion of the reference frame. So you either need to consider the accelerated motion of the reference frame and say, okay, that makes sense because we've got accelerations going on. Or or you can think of there being a fictitious force. Okay, so So this or part is for both of this, right? A fictitious force actually needs to be drawn in a non-inertial reference frame. Okay, you need to actually draw that fictitious force in a non-inertial reference frame in order to have it actually make sense. And I'm going to be showing you examples like that. So just point form from this, obviously, non-inertial reference frames are accelerating. And so you, I suppose, need to answer the concept question about this later on, where you're as you do more examples, I feel like as we do more examples of this, you're gonna these words are gonna make more sense to you. So I don't want to dwell on this page for too long. Is anybody jotting down point form of this and need some time? All right. So here's an example to help make sense of all that stuff. If you're in a car that's slowing down and you look and you notice a 0.2 kilogram apple accelerates at 3 meters per second squared off of the seat that's beside you, right, and onto the floor, right, without anything touching it to cause acceleration. No one's sitting there like tossing the apple forward onto the floor. Instead, the apple just went forward onto the floor. From in that reference frame, it seemed like it did it on its own, right? So the question is, what force caused the apple to accelerate at 3 meters per second squared relative to you in the car? What force? Been following along the concepts here? What force actually caused that acceleration? So you're driving along in a car. Go ahead.
Is it the inertia?
Yeah, and so the answer, you're right, it's inertia of the apple itself. The answer is what force? Well, there isn't a force, right? There isn't a force at all. The apple was really just traveling at a constant rate, and the car was actually slowing down, right? So what's happening is you've got an apple that is traveling along at this same velocity. So let's say like velocity here and velocity here, right? They're going along great, right? Well, if all of a sudden the car slows down, then it's going to fall behind so picture it, it's falling behind where the apple would get to, and so you notice the apple went ahead, right? So basically, the original position of the apple and then the new position of the apple, right? As a result of that little demo that I sort of tried to do there. Yeah, so there isn't a force at all. You can calculate the value, though, of the fictitious force. Easy. You'd be like, well, it has a mass and it has an acceleration, so there's a fictitious force on this apple of 0.6 newtons that actually makes it accelerate forwards in that reference frame, right? That force doesn't exist in reality, but you can talk about the size of it. You can label it on diagrams, and it will make sense within those diagrams. Okay, as long as you're labeling things and doing things right within those diagrams, that it actually does exist. Or at least it makes sense to draw it. So I'm going to show like the apple was there, and it basically kept going forward as this thing slowed down, as the car slowed down. So what does a free body diagram look like? Okay, so for the apple in the car, relative to the Earth, you've got it's actually, I don't even want to put any on here at all, but vertically, right? Vertically in the y direction, you've got the normal force and the gravity force. So in the y direction, that's what you have. In the x direction, there's no forces at all. Right? F net equals 0. There isn't an applied force needed to keep it going. There isn't any air resistant drag force. There's no forces at all. So there's actually, saying F net equals 0 isn't actually good enough, but it basically equals all these forces added up. I want to point out that there aren't any forces needed. So that scribble there says there's no forces needed for constant velocity. So the free body diagram would maybe be better to list as, give me a second here, might be better to list the free body diagram just as, without the green stuff, just like that, right? There's no forces at all needed. Okay, So this is like extraction forces, right? So it might be easier to think of it that way. Because it's just inertia that makes the apple fall on the floor, right? The new part for us is to be able to draw a free body diagram and have it make sense to us, where you're going to have the free body diagram for the non-inertial reference frame. Okay, so this free body diagram over here was relative to the Earth. This one's going to be relative to the car. So relative to the car, right? We have our, so if since I have it there, I could still put that in. It's up to you if you want to think of it that way, but basically, vertically things are still balanced. Horizontally, towards the front of the car, we actually have a 0.6 Newton perceived force, right? We have a force that pushed the apple onto the floor from that point of view within the car, right? In fact, if you were the apple, you would have had to like hang on, I guess, to not fall on the floor, right? But of course, apples don't have hands, so they can't hang on. So it does make sense in the context of this free body diagram, right? The non-inertial reference frame free body diagram. It does make sense to draw that number, even though it doesn't exist. We can still say, oh, well, it accelerated forward. You can tell in this diagram here, you can tell there will be acceleration, right, relative to the car, or relative to the NIRF. Have I said that yet? I think I did on the other page, right? NERF. I actually came back to a lesson like a while after having mapped it out and everything else, and I was like questioning myself. I was like, what's NERF? I had forgotten that I used that acronym. But anyways, so here, there will be acceleration relative to that non-inertial reference frame. That's why there's a force. You can see it, right? So I feel like maybe color coding that. Red, just to sort of show like it's the red force that's leading to that. So there's acceleration. So I guess to have this one equivalent for the apple and so on relative to the Earth, you kind of have to show, that there is. I guess you don't have to do anything here. I just basically it's constant velocity, but it falls onto the floor. Like you see, even though this fictitious force is kind of doesn't exist, you can see the value of this free body diagram because the motion actually is included in the diagram, whereas this one, not so much, right? It falls on the floor, but no forces involved. So the next level here then, yeah, I was going to go to, oh, that's what happened. On the wrong page here. There we go. So the next one's actually here. I was going to say I was going to go to one where I have a ball hanging from a string in your car. Okay, so picture an object hanging, it's supposed to say hanging, in a car that has an acceleration. So you're in a car and you put on the gas and you're accelerating forward. Acceleration AX here in the X direction. And the acceleration makes the ball hang backwards. You can picture this, right? Something dangling from the rearview mirror. If you accelerate fast enough, you can see it sway backwards. So the free body diagrams for these guys, obviously we could have a free body diagram just like this. In the inertial reference frame, the only forces on that object hanging there are a gravity force and a tension force, right? Those are the only forces, Ft, right? And so for the inertial reference frame, you have an acceleration, so you actually have a net force. That net force would be from the tension force X component, right? That's the force forward. So if you were analyzing that out, you would say what here? You'd say in the X direction, there is a force on it. There's a net force. So there's an acceleration. It's actually accelerating forward. This isn't the Apple question anymore. This is the car is actually the ball is actually accelerating rather than maintaining uniform motion. So slightly different type of example here. View, zoom, entire page. All right. So what does the non-inertial reference frame look like? Okay, so we're going to include a fictitious force with this one. Basically, this one, if someone looked at that ball hanging and swaying backwards, they might think, ooh, there must be a force on that, right? There must be a fictitious force that's applying backwards on this thing to make it hang like that. Okay, in the reference frame of the car, if you didn't know the car was accelerating, there'd have to be a force pushing on it, making it deflect out at a 10-degree angle, right? So that fictitious force here, let's make that thing purple actually, and so on, includes a fictitious force like that in this case. So I almost think maybe I better make a new one of these over here for it. So I don't have something listed, because I don't want to have a force listed on there for the other one. There we go. So this is the idea. So our free body diagram is going to look like that. We're going to have this applied force, this fictitious force that doesn't exist, backwards on it, right? What does that imply? Like that free body diagram makes sense in terms of something, just like this free body diagram makes sense in terms of something. So this one makes sense where you're saying it's actually accelerating relative to the Earth. It's got an applied force, the green one forward on it, right? It's got an F net equals ma, and put that applied force forward in action, and you can figure out the acceleration. What does this net force diagram tell us? And I need to clarify here that this force and this force are balancing out to nothing. Okay, so if the net force and these are also balancing out to nothing, so F net equals 0. What's that telling us?
If F net not accelerating relative to the car.
You betcha. Good job. Okay, so that's showing us no acceleration relative to the car. So this would make, what do I got here? This would make a, oh yeah, sorry. So let me undo that, because I'm gonna do that, but I thought I had this in here. So it makes sense. It's logical relative to the non-inertial reference frame, i.e. It's not accelerating relative to the car, that non-inertial reference frame. Great job. Okay. So this is logical, just like this one's logical, just in different viewpoints, right? And so the thing I want to point out to get us ready for when we get to the circular motion stuff is that you could name this force, right? We don't, but we could, right? If we really, were convinced, like in the car, it'd be like, oh, so that magical force that's pushing that ball backwards to make it hang at an angle, we could name it. It would make it feel like we know it better if we named it, right? So we could call it an anti-acceleration force. We don't, but we could. We could call it a resistive force, whatever. So I just need you to recognize that I think everybody's okay with the idea that you understand why we don't do this, right? We don't bother, right? Because it's like we get it that the car's moving. You can clearly tell, the car's accelerating, and this is what's causing it to sway and swing the way it does. The issue that I need you to be okay with when we get to it is that it's exactly the same as what they do in circular motion. Okay, even though no one in the right mind would name this thing an anti-acceleration force or whatever, it's too obvious what's going on. It's exactly what people do with circular motion. Okay, so in circular motion, I was wanting to bold it, but I guess I'd have to unbold the other one. So I wanted to emphasize, right? That's exactly what people do with circular motion, is they call it a centrifugal force, right? Some people pronounce it sort of slang as centrifugal force, but centrifugal force is the properly pronounced version of it. Okay, so naming that thing seems ridiculous. I hope you agree, right? To call it an anti-acceleration force. And so really this centrifugal force is equivalent to that when we get to circular motion in full detail. And I hope that helps you sort of understand circular motion when we get there and put all the pieces together, right? So yeah, so we can actually determine the acceleration. This is just sort of review at this point, sort of, except we haven't done a question like this, but it's the same as what we've done in the past, right? So in the y direction, we have acceleration is 0. That's actually a y there. I was looking at it sideways myself too. Anyways, in the y direction, it's 0. The acceleration is 0, so the net force is 0. So in the y direction, we've got forces. We've got a gravity force, and we've got the vertical component of the tension force, right? We're told that that's 10 degrees here, which is going to force this angle down here to be, I guess, 80, right? So if I'm talking about the vertical component, I'd want to say either sine of 80 or cos of 10, I guess, whichever would work. Okay. But main idea is we know the tension force y component is going to be equal to the gravity because we know the acceleration in the y direction is 0. So I did use cos of 10 in my numbers there. If you feel better about using this as your angle, then you just have to use sine of 80, which would be the same thing. But yeah, so that would, that would give us values. Now notice that this is giving us, because we don't know the mass, it's giving us, a number in terms of m, right? So notice that this equation here, you could call it equation 1 and say, oh, that equation has 2 unknowns. What do you do if you're looking for, solving this, right? You need to find the second equation, right? You need to look for that second equation. So obviously we got our first equation from the y direction analysis. Our second equation is going to come from the x direction analysis. So x direction stuff. X direction stuff. We know the net force equals the only force in the x direction is the x component of the tension force. We know that we have values, right? We've got angles and so on. So the x component, we can say, oh, it's ft sine of 10. And we know that net force is always equal to mass times acceleration. We were told what in the first case here has a horizontal acceleration. Oh, it has the angle, right? That's what we were actually given. We're given the angle. So in this question, we actually have the tension force plugged in as 9.95 m, right? So that's the substitution point here. This is where maybe it would be better if I showed, just to emphasize the idea of what we did here. This question, I feel like I want to be able to say there's the other equation that has 2 unknowns, but so there's the 2 unknowns. But the acceleration one, it's bugging me that that's missing in there. Tension, mass. How do I explain that to you? Oh, because the masses cancel out, right? So yeah, the masses cancel out. So your 2 unknowns were really the acceleration and the tension force. But you can see that it works, right? That tension force can plug in, masses cancel out, acceleration solves for 1.73 meters per second squared. I don't know if I want to leave this in talking about in terms of 2 equations, 2 unknowns. It's kind of a little bit different than that. Oh well. So please look at this as like, yeah, this is what we've been doing all in grade 11 and reviewing now. Acceleration in y direction is 0. So I know my net force, all the forces added up, is equal to 0. That leads to something that we know is true here, right? Leads to that tension force. The x direction stuff, we know net force equals ma. If we're looking for that acceleration value, we got ma. And we know the only force in that direction is the tension force in that direction. So the component stuff from grade 11 kicks in. Plug the 2 numbers together, figure out your acceleration. Right? So that's just a calculation that, if you had one of these questions thrown at you without seeing it worked out, I could get that being challenging, right? If you're given the mass, it makes it seem easier because you would have been able to calculate out a number here. Oh, the tension force, I know the number, yay, right? So then you'd be able to figure out the tension force and set it equal to ma and solve for the acceleration, right? But when you don't have the mass, it seems weirder, but that's just a reality of things. So this is what we're leaning towards. Uniform circular motion. it's not quite tomorrow's lesson, but close to the second one after tomorrow, whatever. We're going to look at quantitatively analyzing this. In other words, numbers to do with it. But this is the situation. I want you to visualize like the speed being the same the whole time. Okay, round and round. It's going at a whatever speed, 20 meters per second or something. So now it's 20 meters per second to the left, down, 20 meters per second to the right, 20 meters per second up, 20 meters per second at an angle. It's always just round and round, right? So the speed's constant. Acceleration in this scenario is always towards the center. If you think about it, the acceleration is perpendicular to that motion always towards that center. If it was like tied by a string, for example, I'd be pulling towards the center. And so it only changes the direction. It's not changing the speed. It's just changing the direction. It's making it travel in a circle. So that's how we make uniform motion, circular motion happen. It's by having a force perpendicular to the velocity. This might seem familiar to the, so I'm going to say just like the Fm, the motor force, right? So Fm was what, QVB sine theta? That was a force, a magnetic force on a moving charge. There might be another version of the equation as well, but basically if you had an electron zipping along and it's going into a magnetic field that is, say, into the page, when the electron's inside here, it actually has a force down. If you look at the, oh wait, no, up. It's going to have a force. Yeah, it was down. Thumb in the direction of electron flow, fingers stretched out in the direction of the magnetic field, and so there'd be a magnetic force down. Right? And so we talked about in the electricity magnetism unit, we talked about how we would travel in a circle. So there's a link between our previous unit and this concept. Anyways, so we, yeah, this animation, we have to wait for it to happen here, I think. It's going to have a car going along with a blue person and a red person. And the blue person ends up getting pushed to go in the circle. So imagine the red person, the red dot, being a seat belted in. They're saying the door pushes on the red person. And then the red person pushes. This isn't as good of an animation as the one I used to have in the lesson, but Flash doesn't work anymore. So this is the best one I could find. So you want to visualize the blue person would just continue in straight motion, but ends up getting pushed in the circle by the red person. So this is, you're driving along in a car and you turn really fast and you sort of slide over, hit the person beside you if you didn't have your seatbelt on, I guess. No one does that anymore anyways, but so that's the idea, right? So the force felt by the blue person, the blue person would feel like they're getting thrown outwards, okay? If you're turning a corner really hard, the blue person is going to feel like they're thrown outwards right about now. And then they get held in place by the red person. So what's really going on here, the held in place by the red person gives you, you know, that actual applied force that's towards the center. So this one is fictitious, right? This is the fictitious force. So it doesn't really exist. This applied force by the red person in the direction of the circle is the real force. So recap, I don't think we need to recap at this point, but you know, we have the inertial and non-inertial definition, right? So I'm just starting to get you thinking about circular, and I'll pull back a little bit from it. We've talked about this bottom part here. The fictitious force we've already talked about was that apparent weight stuff. And I just want to remind you of that, okay? That in the elevator situation, right? If you're using this is the elevator that's accelerating upwards, okay? The inertial reference frame, the regular reference frame relative to Earth, has a normal force of 541 and a gravity force of only 491, showing a net force up, and we know it's accelerating, right? In the non-inertial reference frame, you're not accelerating relative to the elevator. And so that has to be, you'd have to include a non-inertial reference frame, like a fictitious force in there. So that this force, the 541, would balance with that. So this is the feeling that you'd feel like you're being pushed into the elevator floor when it's accelerating up, right? So that's the fictitious force that we've already talked about, to remind you of that. Okay. Anyway, so the idea of including these fictitious forces continues for us, right? So the inertial reference frame for this circular motion stuff, back to the one we're trying to tackle, would just be that. You've got a force towards the center, right? So the actual force is towards the center. It's provided by the normal force inside the ride, or the string that's holding it to the center, however you want to think of it. If this is like an amusement park ride and you're buckled in and whatnot, the normal force, or the seat or whatever in the ride, is going to be pushing you towards the center in order to make you travel in a circle. That's what's really going on relative to the Earth, right? That force is called the centripetal force. Okay. We actually have already used the equation for this because I gave it to you in the context of the electromagnetism, mv squared over r, but we'll develop that one too so we can get a better feel for why it's true. So the actual force is towards the center of a circle, as I've talked about. You can even put that, that force there. See how there's a force, there's an acceleration towards the center, and there's a force towards the center. F equals ma. Right? It's actually accelerating towards the center. There's actually force towards the center. It's called the centripetal force. Unfortunately, the general public don't understand the physics of circular motion, and so this centripetal force. Notice the spelling there. That's not a spelling mistake. Centripetal force. If you're sounding it all out, that's the force that's really going on in circular motion. Okay. The one people refer to is this situation, right? In order to explain zero acceleration relative to the ride, so acceleration equals 0 relative to the ride or the car that you're in or whatever, right? And so you can see in this diagram, you've got a net force of 0, right? As long as you have this fictitious force, okay? That fictitious force is the one that people call centrifugal or centrifugal, if you're pronouncing it fully, okay? Centrifugal force. So that's the force that you kind of feel like is acting on you in that non-inertial reference frame. And it's not that you kind of feel like you literally feel like you're being pushed outwards in the ride. What's really happening is the ride is pushing inwards to make you travel in a circle. Okay, so the feeling you have in that ride is because of your inertia that wants you just to travel in a straight line. Okay, so centrifugal force, that center fleeing force, it means, doesn't exist, but it makes a lot of sense to draw it in certain contexts, right? Where you're talking about the free body diagram for that non-inertial reference frame. So if you're dealing with non-inertial reference frames explicitly, you absolutely do list those forces in there. What's going to happen is we would calculate this force as a number. That's our mv squared over r number that we'll talk about later, but whatever. And so then you could say, oh, so then the force you're feeling is equal to that, because you have a 0 acceleration to the ride, net force means 0, and so on. Like you can actually calculate and reason out that the centrifugal force that you're feeling is a very calculatable value. Any questions about that? So new word for the vocabulary, centripetal force, centripetal force. So this video is so old, but it's so good, and it's so not available. Luckily, I have it as a service to YouTube. And we'll watch a bit of it. Relative frames of reference. frames of, as long as I've typed it the same way. Relative frames of reference, 1960, 2.2 and 1.2. Which one was it? 1, 2. 1, 2. Not sure what the difference is, but it your head might start to spin a little bit, literally, but it's pretty good. I have to figure out which part I'm going to skip forward to here, but I think sound does kick in eventually too. So he's trying to get you thinking about relative reference frames and so on, right? So you're watching this video, assuming he's just standing there talking to you like normal. And then this other guy comes in. Toss for it. I so want to see a remake of this in like new quality, but so the first bit of this is just to get you well aware that your reference frames can mess with your interpretations of reality, right? And so the fact that you think and you feel like there's a force throwing you out to the outer edge of the circle is totally understandable. Mm.
Mr. Horn, I'm not sure if it's just me, but I can't hear anything. If it's just me, I'm sorry, but...
Oh, goodness. That's because
Okay.
I unplugged the microphone in order to plug in my USB stick. Board right now. So,
okay, sorry. I just thought it was my internet, but...
So I was at least, I was annotating or whatever, whatever you call that. For at least, but you know, so he's standing here talking to you, and you assume that he's just like normal, and then this other guy's like moving around weirdly, and then it turns out they decide they're gonna flip for it to see who's really upside down. This guy flips the coin, and it goes up and down into his hand. This one goes, you know, down and falls on the floor, right? So, anyways, they figure out that it was hanging upside down. So it's all about reference frames being misleading, depending on what you've labeled as your reference frame you trust. So if you're labeling him and this little reference frame he talks about as the one you trust, and you see motion, you're assuming like, oh, he must be moving, right? Turns out the wall was moving backwards. And so really getting you thinking about reference frames being something that'll trick you. So hopefully...
All motion is relative, but we tend
you hear him now? Old school,
yes.
All relative?
to think of one thing as being fixed and the other thing as being moving. We usually think of the earth as fixed, and walls are usually fixed to the earth. So perhaps you were surprised the first time when it was the wall that was moving and not Dr. Hume. A frame of reference fixed to the earth is the most common frame of reference in which to observe the motion of other things. This is the frame of reference that you're used to. The frame is fastened to the table. The table is bolted to the floor is anchored in the building, and the building is firmly attached to the earth. Of course, the reason for having 3 rods is the position of any object such as this ball can be specified using these three reference lines. This reference line points in the direction which we call up, which is a different direction here than it is on the other side.
That was new info back in the 60s.
And these two reference lines specify a plane, which we call other frames of reference, moving in different ways relative to the Earth frame. Well, let's look at a motion. This steel ball can be held up by the electromagnet. Now I'm going to open the switch and you watch the motion of the ball. The ball is accelerated straight down by gravity along a line parallel to this vertical reference line. As you can see, the electromagnet is mounted on a cart that can move. I'm going to do exactly the same experiment that Dr. Hume did, but this time, while the cart is moving at a constant velocity. The cart is pulled along by a string which is wound around this phonograph turntable, and that pulls it with a constant velocity.
Phonograph turntable? It's a record player. That's so awesome.
When the cart passes this line, the ball is released, as you can see. I'm going to start the cart down at the end of the table so that by the time it gets to this point, I can be sure it's moving with a constant velocity. I want you to watch right here so that you will see the ball falling. I think you can see that the ball landed in exactly the same position that it did before when Dr. Hume did the experiment with the cart fixed. But this time, the ball could not have fallen straight down. Let me show you why. The ball was released. At that point, if it had fallen straight down, because the cart moves on and the time it takes the ball would have landed back here somewhere.
So we actually saw it, of course, travel with projectile motion down to that same spot, right? So it was released here, falls like a projectile down to that spot as the cart moves over, is what he's getting at. So I want to skip ahead to the circular motion part. Where did we get to? That's just slow motion of that, projectile motion, all good. Let's get to the circular motion stuff.
As far as you're to one another,
Okay, where the circular motion part is.
you probably see the spot moving in a circle.
Yeah, let's go
Moved
ahead.
along with when the motion is.
All right, here we go.
Now we're going to do another experiment on relative motion to show how to compare the velocity of an object in one frame of reference to its velocity in another frame of
Oh,
reference.
it's the circle one, I forget
If I give
when it
this
starts.
dry ice puck a certain start, it moves straight across the table with a speed which is essentially constant because the forces of friction have been made very small. This is just the law of inertia. An object moves with a constant velocity unless an unbalanced force acts on it. Now, will you give it the same start backwards? Dr. Hume gives it the same start. It moves back in this direction with the same velocity. Now, we are on a car here, a car which can move and which really is going to move in this direction. And we're going to repeat the experiment. All right, let's go.
So the car is moving to the right, but it's still able to do the same stuff. So that's the idea of this being an inertial reference frame, right? Because it's still going to behave the exact same way, even though the car is moving to the right with constant velocity.
If we were making measurements here, then we would observe the same velocities, that is the same experimental results that we did before. And so would you, because you are observing this experiment through a camera which is fastened to this cart. That is, you are in the moving frame of reference with us. But now we're going to do the experiment again, and this time you watch through a camera which is fixed in the Earth frame of reference. So concentrate on watching the puck. Don't let your eye follow us. I think you'll see that it'll move faster that way and not so fast this way, relative to you and relative to the wall behind.
That's awesome.
And so would you, through a camera,
So
which is
there
a
you go.
moving frame
see
of
again.
time, you follow us. I think you'll hear frame of reference.
So watch it going
So
quite
concentrate on
fast
watching
relative
the
to the
puck. Don't let your
rectangles in the
eye
back.
follow us. I think you'll see that it'll move
And then
faster
slow.
that way and not so fast this way, relative to you and relative to
So
the
that's the
wall
same as what we
behind.
saw last time. And then
We were sitting on the car to Hume this section, the same the plus.
so this one
minus
doesn't get
anything
actually.
about
There's
this
another one coming
expression.
up that'll get into
It's the
circular
velocity
motion.
of light,
So that was just
the
about
ideas about relative motion.
relative motion being misleading. Okay, so I'm going to save the circular one probably for the next lesson when I talk about circular some more. Is that right? Down here? Oh, this one. Yeah. Yep. All right. So that's pretty much our time for today. There's the questions to do with non-inertial reference frames. Those ones. Take a peek at those, remind myself. A lot of it's ideas rather than calculations. Some of it is calculations, though. Anyways, give those oral, and let me know if you have any questions. All right.